Okay, like I said, we're going to learn some new words today. And so section 1.6, the big word that we're going to learn in this section right here is called polygon. It's really not even the title of this lesson. The title of the lesson is two-dimensional figures. All right, but a two-dimensional figure, one of them anyway, is a polygon. This is what we're going to concentrate on, is polygon. Let's take a look at what this word means. Look at the word poly. Okay, poly means many, right? The gon is kind of talking about angles, so it's talking about many angles, so something that has many angles. Well, there's a lot of things that have many angles, but what specifically is a polygon? Let me just grab one of these shapes I already have made up and put that right there. Make it a little bigger. This right here is an example of a polygon. Let's see why it's a polygon, because not every shape is a polygon. This happens to be. Look what it's made up of. It's made up of line segments. So a polygon has to be made up of line segments. Every single one of these things right here are line segments. And they have to intersect each other at the endpoints of each of the line segments. Do you see that? Which means, let's see if I can watch this. If I took this segment right here and extended it, that technically would not be a polygon. All right, because this line segment right here does not intersect this other line segment at its midpoint. All right, if it or not midpoint, but endpoint. I'm sorry. All right, so they got to intersect each other at the endpoints. This one doesn't. It intersects somewhere in between here. All right, so that technically is not a polygon. Now that would be a polygon right there. All right, because it intersects at the endpoints. Everybody see that? Each one of these segments right here is being intersected by the other one at its endpoint. So they hit each other at the endpoints. Make sense? Also, they're line segments, so there's no curves. Okay, there's no, there's no this kind of thing on here. They're all straight. All right, they're all line segments. What else? It's got to be closed as well. All right. For instance, if I let's see if I can do this. If I did this, still everything's a line segment, right? But look, two things are wrong with this. First of all, this doesn't intersect anything at its endpoint. Nothing's intersecting this endpoint right here. Right? And it's open. Look at that gap in between here. So that means that's not a polygon. But that right there is a polygon. We okay with that? Pretty easy. Let's go a little bit further with this. And let's do this. Let's take each of these line segments right here. And what I'm going to do is I'm going to extend each of the line segments. And I'll tell you, I'll do this like this. Watch. Extend that side and extend that side. See what I just did? Now what I want you to see is this. I'm going to take this line segment and I'm going to extend it this way a little bit and this way a little bit. I'm going to do the same thing for all of these line segments. Now in my other class I took these line segments and I drew dotted lines to show where they extended, but I think this might be a little bit neater and easier. Should have done this in the other class, but and then this goes like this. See what I did? I just took all the extensions. Now look, I got all these pieces sticking out of it. But are any of these pieces that are sticking out of it actually go inside of this polygon? No, none of them do, okay? This polygon's still nice and clean inside of there, right? All those extensions, none of them came around here and went inside the polygon. So when you have a polygon like this, when all the sides, if you extended them all out, they all eventually will intersect, but they'll intersect outside the polygon. They never go inside the polygon. So if the inside of the polygon is nice and clean, we call this a convex polygon. All right, so write that down. A lot of new words here. This is a convex polygon. All right? You say, well, what does something look like if it's not a convex polygon? Well, I'm glad you asked because I happen to have one right here. And let's scooch this down. Let's make this a little bit bigger. Now look at this thing. Now what if I extended all the sides to this? Watch. What if I extended? I'll tell you what I'm going to do. Let me do something here. Just want to see if this will work. I don't know if this will work or not. Copy, paste. And then I'm going to put this right on top of it. Right there. Then I'm going to make it a different color. Make it this Oops, what did I just do? There we go. Well, you can kind of see it. Now watch this. I'm going to take this and extend it. Alright, I'm going to take this side and extend it. See that? Now, so far, are those extensions going through the inside of this polygon? No, but guess what's going to happen here? If I take this side and extend it, watch. Whoops. There we go. Look, if I extend that, but watch here. If I extend this, guess what it's doing? It goes through it, doesn't it? Alright? As soon as it goes through it, it means it's not a what? Well, it's still a polygon, but it's not a what? It's not a convex polygon. And look, the same thing will happen with this. If I extend this out, see how it goes through it? So this part right here and this part right here is actually going through the inside of that polygon. So we don't call it a convex polygon. We call this a concave polygon. Alright? Writing all this down? Should be writing this down. Should be taking notes. Shouldn't just be sitting there doing nothing. Everybody should be writing. Every class period, every time I write something up here, you should be writing this stuff down. So this is a concave polygon. In the grand scheme of things, it really doesn't make a huge difference on whether you know the difference between a concave and a convex polygon. But there are a couple things, a couple definitions that we'll have a little bit later that talk about, okay, this only works with a convex polygon, or this works with a concave polygon. And so you just have to know what those words mean. That's basically all we learn that for. All right, so now you know the difference between convex and concave. Let me grab another polygon. Let's take this one right here. And let's drop down a little bit. Put that right here, make it a little bigger. Let's look at this one. Alright, this is a polygon as well, but this is more of a specific type of polygon. Now, I made this like last year, okay, and I made sure that all these sides are exactly the same. Alright, you could sit there and measure them if you wanted to. We're not going to. Just take my word for it. But all of those sides are the same. There's 5 sides. All 5 sides are the same. If you have a polygon and all the sides are equal to each other, okay, so let's write that down. If all the sides are equal to each other, we call that an equilateral polygon. All right, so say it's equilateral if all the sides are equal to each other. And I also made this so that all these angles inside of here are going to equal each other. So this angle, this one, this, and the last one. I put arcs. I put one arc for each one of those. Okay, so all those angles are equal to each other as well. So if all the angles, I'll just shorthand that, all the angles are equal to each other, we don't call it equilateral. What do you think we call it? Equiangular, right? Because they're angles, okay? Equiangular, right? Equilateral, because lateral means sides. Did you know that? If we talk about lateral, it means sides. Then angular, of course, is angles. So if all the sides are equal, we would call it equilateral. If all the angles are equal, we could call it equiangular. Now, I made this thing so that both of those things are true. Okay, we'll get to that in just a second. I made it so both of these things are true, but I could have made it where all the sides were equal, but the angles were not necessarily equal to each other. Okay? And I could have made it where the angles were all equal, but the sides were not all equal. I could have done that. I didn't. All right? Take me a little bit more thought and process to do that. But what happens if both of those things are true, like this thing right here? So if both things are true, if all the angles are equal, and if all the sides are equal, okay, if both of these things are true, we call this thing, now you'd think you'd get a better word than this, but we call it a regular polygon. Right? You had such cool words up here, equiangular, equilateral, and then they just say, oh, it's just regular. It's just a regular old polygon, nothing special. Well, it is pretty special. Even though it's called regular, it is a pretty special polygon. We're not going to do too much with a regular polygon in this lesson. In fact, there's another chapter. We're going to do a ton of stuff with this. In fact, if I told you this is a regular polygon, I could actually figure out what each of these angles are actually equal to. All right, we're going to come up with a little formula and all that kind of stuff, but we'll do that in another chapter. We're not going to hit on that in here. So there is a lot of stuff that we can do knowing that it's a regular polygon. But today, all I care that you know is what a regular polygon is, what an equilateral polygon and what an equiangular polygon is. All right? Everybody good with that? Pretty easy. Today's, for the most part, today is just kind of vocab kind of stuff, just learning different words to different things. Let's do this before we move on. Let's label. Tell you what, I'll copy and paste this. Let's learn how to label a polygon. You know how you labeled like a point, a line segment, and all those kind of things, angles. All right, we learned how to label all that stuff. So let's call this A, B, C, D, E. All right, how do I label this thing? Well, there's no fancy like symbol for polygon. So we just write the word polygon. It's kind of boring, isn't it? So we just say it's a polygon, but we got to name the polygon. By the way, I almost forgot to tell you this. Wow, at least I'm remembering. These things right here, these line segments, are called the sides of the polygon. I hope that makes sense. And what do you think the point is right here? It forms an angle, so what would this point be on that angle? It'd be the vertex, okay? And it's also the vertex on the polygon, all right? So the points, okay, but there's not just one vertex here. How many are there? In this one, there's 5 of them, aren't there? All right, so we call that the vertex. Now, if we're going to go plural, if we're going to say more than one vertex, we don't say vertexes. Anybody know what we call that? Right, that's it. You call it vertices. You got it. Okay, vertices, that's plural. Put PL next to it for plural. Okay, so it's one vertex and 2 what? Vertices. Good. All right, so there we go. I needed to make sure we said that. Now, look at this. I got to name this thing. Do I have to start at A because A is the beginning of the alphabet? No, it has nothing to do with that. I could have used all kinds of random letters here, and it doesn't matter where you start. You could have started anywhere on here. Just to make this, though, nice and neat, we'll start at A. Is that all right? So I'll call it polygon. Now, I'm not just going to say polygon A. What I'm going to do is I'm going to list all the letters in this polygon. But I can't just do it in some random order. I got to go in some kind of an order. I could go around this way, or I could go the opposite way. But I have to go with the consecutive vertices. I can't go A, then D. You follow me? I can't skip one. I got to go to the next one. I can't go A, C, and then jump over to E, and jump over to B, and then D. I can't do that. So if I start at A, I could go 2 ways. I could go to B, or what else? I could do what? I could go to E. So let's go to the right. Let's go this way. So if I wanted to call it, I could call it what? Polygon A, B, C, D, E. Seems like a long way to go about it, but that's what we call that polygon right there. It's got 5 sides, it's got 5 vertices, and I got 5 points right there. Okay, that's how I name it. No fancy symbols or anything. Just put the word polygon and you call it A, B, C, D, E. Okay, or if you wanted to, I could call it, I could sit here all day almost and name it a bunch of different things. But let's say we started at A again. What else could I name it if I started at A? Very good. It could go the other way. So I could go A, E, D, C, B. Now I don't have to start at A, do I? I could have started at any of these points. So I could have started at B if I wanted to. I'm not going to write all these down. But if I started at B, I could call this polygon what? B, C, D, E, A, or go the other way, call it B, A, E, D, C. And I could start at C. I could have started at D, could have started at E. Does that make sense? All right. But I can't like skip across one. All right. I got to go in order, either one way or the other way. And that's how we name polygons. All right. Let's continue with polygons. We had different names for polygons. Let's make a little chart here. Write this down. We have the left side is name or sides, and the right side is names. First of all, what's the lowest number of sides I can have to have a polygon? 3, that's right, because I can't have 2 sides, because look, if I had 2 sides, even though that they connected right there, is there any way this could be a closed figure with just 2 sides? No, there's not, okay? I mean, I could take this and then like maybe swing it around like this, but then it's not a polygon, is it? Okay, because it's really not making an angle, because that angle would be 0. So there's no way with 2 sides that I could make a polygon out of it. So the lowest number of sides is 3. It's a closed figure, yes. Right? That's what we said earlier. It has to be a closed figure. All right, so sides. So 3 is the smallest one, and we have a name for that. Talk to me. It's a triangle. All right, so we name it a triangle. Let's list a bunch of them. 4. Now, a lot of people look at this and say, what would you say, Josh? A square. Okay, a lot of people would do that. They'd say square. They say rectangle. But not every 4-sided figure is a square, is it? Not every 4-sided figure is a rectangle. Not every 4-sided is a rhombus. We'll talk about rhombus and square and rectangle in another chapter. But every 4-sided figure is a quadrilateral. You ever hear that before? Okay. So no matter what, for instance, let's just draw one. Here's 1, 2, 3. I'll pretend it connects. All right. 4. Let's make this actually connect. That's good enough. All right. That's not a square. It's not a rectangle. It's not a rhombus. It's not a trapezoid. You ever hear a trapezoid? We'll talk about a trapezoid another time. It's not a parallelogram. We'll talk about parallelograms. But it is a what? Quadrilateral. It's a quadrilateral because it has 4 sides. Doesn't matter what the shape of it is. All right. Doesn't matter if you have right angles or don't have right angles. 4 sides, quadrilateral. Got it? So is a square a quadrilateral? Sure. If it's got 4 sides, it's quadrilateral. Is a rectangle a quadrilateral? Absolutely. All right. Get the idea. Let's go 5. 5, famous building in D.C., Pentagon. Right. Okay, so, and that's why they call it the Pentagon. They don't call a 5-sided figure a pentagon because of the building in D.C. They call the building in D.C. a pentagon because that's what it is. 5 sides, 5 angles. It's a pentagon. Right? 6 is a hexagon. I don't know, if you play soccer, if you, at least the old-fashioned balls, they make balls now where they stitch them together a lot different. They got these crazy different shapes and stuff. But those old-fashioned balls where they have those, probably the black and white ones, if you look at it real close, you'll actually see that some of the figures on there are regular pentagons. What does that mean by a regular pentagon? All the what? All the angles and all the sides are equal. Good. And then they're made up of pentagon and hexagons. All right, so look at it. Take a close look at one of those old school soccer balls. I guess they still make them like that. I'm not really sure. But if you look close, you'll see a bunch of pentagons and a bunch of hexagons. And that way, you put them all together, and it makes a nice, perfect sphere, okay, the way the angles are and that kind of stuff. So that's kind of interesting to look at. 7 is not a very famous, I guess, polygon, but I guess you could call it a heptagon. That's what this book calls it. I actually had a book that I taught out of my other school for a lot of years, and they had this list, but they would put 7, they would put as 7gon, right, instead of heptagon. I thought that was kind of funny. They had names for all these other ones, but then it got to 7. It didn't seem like they liked it. And I'm like, I don't really like that name heptagon, so I'll call it 7gon, all right? 8's a pretty famous one. Probably see one of these every day. What do you see? Stop sign, which is a octagon, all right? So it's an octagon. That's 8. 9... You don't hear this word very often, but it's a nonagon is what they call it. 10's pretty famous. What do we call that thing? Pentagon? How about decagon? All right, because decades, right? How many years in a decade?
10.
There's 10. Connie? Connie's daughter. Shannon? Septa is a prefix for 7, yes, but I think this book uses heptagon. But you rarely deal with a 7-sided figure, so that's probably why the other book just said 7gon. But I guess you could call it a septagon. I don't think I've ever heard anybody call it that, but that is a prefix for 7, though. So 11, I didn't know this until I started teaching out of this book, because they always stopped at 10, all right? But if you look at it, I got to look it up again. It's hendecagon. That prefix must mean something. I don't know. I haven't looked it up, but that's what they call it in this book. We'll rarely refer to it at all. 12 is kind of a, it's a little more familiar than hendecagon. It's called a dodecagon. 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 Yep, that's 12. Now you got to stop at some point, right? I mean, if you had like 57 sides, you're not going to have a special name for it. So they kind of stop right there. And then after that, Like whatever, if you had n number of sides, you just call it that number and then put a gon after it, kind of like the old 7-gon. All right, so if you had 57 sides, you call it a 57-gon. I probably wouldn't even call it that. I'd probably just say it's a polygon with 57 sides. That's all I would say. Make sense? All right, enough of that. Let's do this real quick. Let's go back to the, I gotta, oops, I didn't press the wrong button. Let's try this again. That's what I wanted. Yeah, let's go to this. So what's this thing I'm grabbing right here? 3 sides is a triangle. I think this is the first time we've dealt with a triangle this year, isn't it? We actually have a whole entire chapter just on triangles. And in fact, we got another chapter that's just on right triangles. Nothing but right triangles. A whole chapter just on right triangles. All right, so this is our. So we're going to deal with triangles a lot in here. But what I want to do is I want to look at this. I tell you what. You know what I'm going to do? Should have remembered this from the last class. I'm going to put this off to the side a little bit. In fact, I'll just copy it and just get rid of it. I'll bring it back in a few minutes. Let's go to this. What does that look like?
Rectangle.
Yeah, it looks like a rectangle, doesn't it? Okay. Do you remember? We're starting to run a little short on time, but in the other class, we broke it up into squares. Okay, and so you can find out how many squares is in this rectangle. But what we're going to do is we're going to talk about finding the area of a few of these figures. Remember doing that back in middle school? Probably even elementary school. Did you do that in elementary school? I can't remember. Probably what, 5th grade maybe? 4th grade? You did area? Okay, so we're going to do area. What is finding the area of something? Finding the area is finding out how many squares can you fit inside of that figure. All right, that's finding the area. And in the other class, I split them up into squares, and we counted across this way and down this way, right? You know how to do that. But a lot of times, they'll call this one the length and this the width. It actually doesn't matter which one's which. So how did I find, how can I find how many squares? Times 2? How could I find out how many squares? If I split this up into perfect squares, okay, how could I find out how many squares? Take the length, this one, and then do what to it? Times it, multiply it by the width, right? So we learned a long time ago that area is length times width. Is that familiar to you? Should be, yeah. If your teachers did their job, you should be kind of familiar with area is length times width. But what I'm going to do, oops, I'm going to change the wording of that. Is that all right? I'm not going to use length times width. Let's do this. Here's another thing that you could call it. You could call the bottom of it the base, and then this up and down one, what do you think we'll call that? The height. All right, everybody watching? So I could call this the base and the height. So what would the area of this thing be with B and H instead of L and W? Yeah, it'd be base times height. And we usually say base times height. A lot of times we don't even put that little X thing for times. We just put them next to each other. All right, so the area of a rectangle, this is a rectangle, put a little right angle right there. The area of a rectangle is the base times the height. Now, this is very, very important. Watch this. Look at the height and look at the base. They're 2 lines, aren't they? 2 line segments. What's the relationship between those 2 line segments? What do I say? It forms a right angle, so those 2 lines must be what? Yeah, 90 degrees, but give me a better geometry word. Say it. The lines, no, the lines aren't complementary. Lines aren't complementary. Angles are complementary. 2 lines that form a right angle. Come on, we've talked about this earlier today. 2 lines that form a right angle are perpendicular. Right, they're perpendicular, okay? I don't know why that word is so difficult. And the other class had trouble with that too. Maybe because you just learned it yesterday. But these 2 lines, the lines are perpendicular. Lines are not complementary. Angles are complementary, okay? So these 2 lines are perpendicular. The base and the height have to be perpendicular to each other. Did you write that down? And anybody writing this down? I would write that down. That's pretty important. I would write down the base and the height must be perpendicular. So I couldn't do this. I couldn't draw a line like to here and say that's the height, could I? I couldn't say that's the height and this is the base. Why not? Because this length right here is not perpendicular to the base. Make sense? Okay. Now we're going to get to something else. So now we know, so far we know one formula. We know the area, I'll put R. So what does that mean? The area of a what? It's an R. Look at this thing. Come on. It's a rectangle. Yes, it's a rectangle. All right, this thing is a rectangle. So the area of a rectangle, let's remember it as base times height. Is that all right? If you want to go length times width, that's fine. It means the same exact thing. But there's a reason I'm using base and height here. Because of this right here. Watch this. What if I draw a line like that? What did I make this rectangle into? Two what? Say it, Jaden. Two triangles. That's right. Two triangles, didn't I? Now, what looks, just off the top of your head, what looks like could be true about those two triangles? They're both exactly the same, okay? So, if the whole entire rectangle was base times height, what do you think the area of just one of these triangles is? I'll give myself a little room to write. That's right. It's half, isn't it? It's half of the base times the height. Let's get rid of that. So, everybody see that? So that triangle is actually half of the rectangle. If the rectangle is base times height, the triangle is half of that rectangle, so it's 1/2 the base times the height. Does that look familiar to you? So AT, why did I use T? What's up with that? Triangle equals 1/2 the base times the height. Now some people like to write it like this. Base times height, what? Instead of times 1/2 over 2. Either one, it's fine. Whatever you want to use. Okay, so the area of a triangle is the base times height divided by 2. Does that make sense? All right. So now we know two formulas. We know the area of a rectangle, and now we know the area of a triangle. Let me do one more real quick. Just hang on just for a second. Look at this. Does this look familiar? What's this thing? It's a circle. So let's do the area of a circle. Anybody know that off the top of their head? It's not. The area is not 180. The area is not 360. It's pi, right? And then what? Radius squared. Pi r squared. That's area of a circle. We'll continue this whenever we have class next. I know we don't have Monday and Tuesday. So if we have class Wednesday, we'll continue this on Wednesday. And no homework. How about that?